All right, we're going to do our last section before we move into developing models of systems. And so we're going to talk now about block diagrams of control loops. This is some infrastructure related to Laplace transforms that is critical to control. So we're actually going to see some examples here to kind of prep and motivate where you'll eventually be going into control. We don't develop controllers in this class, but material here you see here will be very important here as you move on to the next controls course. All right, block diagrams. So here is a block diagram. You see these are blocks. This is a summer, but this diagram here, it lives in the Laplace domain, but it's very algebraic. It's totally algebraic. So you see here, here's a summer. So we have I of S. So here you have the output. It goes through some filter or something, H of S, comes back negative. So I of S minus O, H of S equals E of S. Now you'll see if H is functionally 1 here, this will be error. Then E of S times G of S equals O of S. So let's play with this algebraic concept here. And so E of S times G of S equals O of S. All right, that's this one. And here we had what the summer was. I minus HO equals E. Okay, so if we move this G over to here, we'd have O over G of S equals E of S, which we know is I minus HO. So I'm going to multiply that G across. And so now I have O times GI minus HO G of S. Okay, so next thing we're going to do is we're going to put the O's and the I's together. So here's GI, here's the I separated, and I brought the O out. So I have O plus HG of S times O of S. And so again, these are all algebraic, so they commute, and so I can readjust the order in here. It doesn't mess anything up. Okay, and so now I'll factor out the O and make a couple other little manipulations. So if we factor out the O, we'll take the 1 plus GH. I'll flip that order. And so factor out the O, bring the 1 plus GH down, and I'll bring the I over to here. So I now have output over input. So this is a transfer function, is G over 1 plus GH. And this is called a closed loop transfer function, CLTF, closed loop transfer function. All right, so, and we can see how that's a closed loop. Here's an input, we take output, we feed it back, and it's running, we have a loop, makes sense. Now we have special names for some other parts here. So this part G of S here, that goes from here to the output, it's called G of S. We always put the G there, but it's called the forward loop. And here's the thing. So it's going forward with the signal. That part makes sense, but there's nothing loopy about it. It's just a straight line through, okay? But tradition is what it is, and this is always called the forward loop. That makes this part the feedback loop. Okay, the feedback part, take something here, bring it back. That makes complete sense, but there's nothing loopy about it. It's just kind of one pass back, but it's called in society, professional, within the controls world, that's the feedback loop. All right, so we want to apply this, and so we're just to show you how this works and kind of some of the stuff that controls do, kind of motivate some of our work here. We're going to do a closed loop control system where we use a forward loop proportional controller. What does that mean? All right. Well, we're going to work with a motor that this is the same motor we looked at before that you apply a voltage to and it starts spinning. All right. But we're going to use it for position control. So we're looking at voltage as output and angular position, or voltage as input, angular position as output. And if you recall, that was an unstable system. But let's see what we have. So there's some voltage, some reference voltage we apply. Should put put an arrow in coming into that. So that will create our, take the voltage, we'll convert it into Laplace. We have our output, so we'll have some sort of sensor that measures position, converts it into a voltage, and we'll presume the transfer function is 1. And so it's going to subtract off from here. That creates the error. We multiply by this k. K is a proportionate controller, so it's just a gain. We can set it to whatever we want. Okay, so E of S times the gain times the motor. Transfer function takes us to, in Laplace, angular position. So that's the system. All right, so here was the transfer function we did before, that for angular position relative to voltage, we added in this S, came in there. And so we noted this was an unstable system. Okay, and we have our gain K, which is just a proportional controller, which we can set to whatever we want. And so let's look at modeling this. So we have E of S is I of S minus the output of S. Okay, G is K times M. Our feedback is 1. All right, so the closed loop transfer function is G over 1 plus GH. The H is 1, so we have G over 1 plus G is what shows up. Then we'll substitute in the transfer function for M here. All right, and now we multiply by S times S plus 10 to clear the denominator, and we're left with 10K over S squared plus 10S plus 10K. And now this is really neat, because you look, these are all positive coefficients here. It's second order system. This is going to be stable. If you go check the roots, they will be in the left half plane, so to the left of the imaginary axis, so it's stable. It has another feature. Look at this, 10K over 10K. If we let S's go to 0, the static gain is 1. So it says if we put a 1 volt step input in, we're going to get 1 unit of final output. So that means we can set the input to calibrate what we get at output. So the system is tracking the input reference that we give. So that's a good thing. All right, so we have no error. OS, our outputs at steady state equals our input. That's a good thing. People like that. And it's always stable. All right, but let's notice some other things. If I let K equal 0, which you wouldn't do because you get no output at the end of the day, but just for sake of math, if we looked, where would the roots be? If I let K be 0, I have S times S plus 10. So we have 2 real roots at 0 and minus 10. So this is sort of a kind of academic concept. Wouldn't really do that and don't get anything out anyway. If you let K to equal 2.5, so 10 times 2.5 would be 25. This will be S plus 5 quantity squared. So we have 2 real roots at minus 5. And so we can see we're here, and then they move in along the imaginary axis, and you have 2 at the same spot. And if you let K go greater than 2.5, you would then have the roots at minus 5 plus or minus 100 minus 40K square root of that over 2. Well, notice if K is greater than 2.5, we have a negative number here under the square root, so we have an imaginary number popping out. So the roots are complex. Well, we can plot this. And if we do that, here, this is the plot. So when K equals 0, we start here, and as K gets bigger, the roots move in until these 2 paths come together when K equals 2.5. And then I'd have 2 roots right here, right at this point. Okay, and then as K gets bigger, 1 goes this way, and then the conjugate going the other. So we can plot the roots as a function of K. From a control point of view, now by the way, we have a name for this plot. You'll learn when you go to a controls course, they'll spend a bit of time on this and teach you how to make these things really easily. But this is called a root locus plot. As you change one variable, you see where the poles of the system move. This is really useful information, okay? Now, so let's see what we have. If we analyze the response for a step input, let's see, as K goes from 0 to 2.5 when the root gets over here, what's happening? So I have a root back here and a root up here, or a pole, okay? This one dominates because it's closer to the imaginary axis. It takes longer to settle out. So I don't even care about this one. So this dominant pole is going from here into this point. So as it goes farther away from the imaginary axis, as k gets bigger, up to 2.5, time constant goes down, settling time goes down. But note the root is real the whole way. So all along here, the damping is 1. So the damping stays 1. That means you get the system is stable and you get a first order looking response. Okay, so it just goes nice and smooth like that. None of this. All right. We'll let k be greater than 2.5. Now look what happens. One pole will be up here, and then you'll have the conjugate down here. So as k gets bigger, here we are, the real part stays at -5. That means the time constant is 1/5. The settling time is 4/5. They never change. Now, as k gets bigger, as this goes up here, what is happening? Okay, if you look at the distance from here to wherever this pole happens to be, it's going to keep getting bigger and bigger. So that means natural frequency gets bigger. If you look at the complex portion, which is just as in going straight up, that's the frequency of oscillation that you would be seeing. So the frequency is getting a lot higher. As k gets bigger, the omega di is going straight up this way. So much higher frequency. Okay. Along this axis, we have damping is 1. Along here, the imaginary axis, damping will be 0. So if you were to track a root, it's going like so. So damping is going down, 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 down. And as it continues to go, it can get to be very, very small. So damping's going down. That means the amplitude of the oscillation is going way up. All right. But here's the interesting thing. K can get as big as you want. You can make natural frequency as big as you want, but it always stays stable. It's still going to settle out at the exact same time. Your frequency could be getting very high with wild oscillation because your damping's low, but it's still going to settle at 4/5 of a second, no matter what you do. It's kind of cool. All right. So what we have here is we're seeing that our overshoot and oscillation, more oscillation, more overshoot as we continue to raise k, while keeping our time constant the same. So if we look at this, let's see what we have here. We start when we're in, if we have our roots right here, both of them on the real axis, this would be roughly what it looks like. It goes to 1, because our static gain was 1. It's done in 4/5 of a second. But then as you raise k, the root pole starts to go up, and you get this oscillation. And as it goes up, you would get more and more oscillation, and this peak would go higher and higher. All right? So this leaves me with the question. Do you really need to solve the ordinary differential equation to understand what the system is doing? And frankly, you really don't. This is, as we've done doing our analysis, once we have our systems, we have a pretty good idea of what's going on, enough that we generally don't have to solve the differential equation. So what you can see here from this discussion we've had, once you really understand the complex plane, you can be looking at something like this and say, well, here's the settling time is 4/5 of a second, but I want to have less than 1/4 of a second for my settling time. That tells you got to move stuff back. And that would be the basis of doing control. Oftentimes in control, you'll have stuff where you'll say, okay, I could accept my damping in the following range, my natural frequency in the following range, what have you. And so you'll have this little zone in here that you need to get the closed loop poles into. That's the basis of designing a controller. And root locus plot will show you kind of where you are, and you can actually design controllers to force yourself into that zone. That's the next class. We're not going to go any further with that, but it's really quite powerful. So with that, we will pack that up, and we will be preparing to start modeling physical systems. We'll see you later.